Hello there, and welcome to the Sleep Porch. Tonight, we are drifting into the vast and powerful world of storms. These are not just passing moments of wind and rain, but enormous natural systems that breathe, grow, and reshape the planet in ways both subtle and dramatic. Storms connect ocean warmth to high skies. They set invisible air into motion and turn quiet afternoons into moments that linger in memory. They remind us that the atmosphere overhead is alive with movement, balance, and energy, constantly responding to forces we rarely notice as we move through our days. As we explore this topic together, you may begin to feel how storms connect distant places, how a single cloud can carry astonishing power, and how the steady rhythms of weather quietly shape life on Earth. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. For now, there is nothing you need to do except rest. Let your shoulders ease, allow your eyelids to grow heavy, and let your thoughts slow as we drift through this remarkable world together. Let's begin. Lightning can heat air hotter than the surface of the sun. For a brief instant, a lightning channel turns ordinary air into something closer to a star's edge than a summer sky. The electrical current surges through a narrow path and forces the air to heat so violently that it expands in a sudden explosive push. That rapid expansion is the real beginning of thunder. A pressure wave born from air, shock heated and expelled outward. In this fraction of a second, the channel can glow brighter than the sun and can branch into countless strands as it hunts for the easiest route through the atmosphere. If you have ever seen a strike and felt your chest flinch a moment later, you have experienced the atmosphere snapping back from that instant of extreme heat. It is one of nature's quickest, fiercest transformations. A single thunderstorm can hold energy equal to several atomic bombs. A thunderstorm looks like a passing cloud, but inside it is an engine that gathers, stores, and spends energy in many forms at once. Warm, moist air rises like an invisible elevator, carrying water vapor upward, where it condenses into droplets and ice. That change releases heat into the surrounding air, giving the storm extra buoyancy and helping it climb higher. Meanwhile, winds shear and collide, building turbulence, spinning eddies, and creating powerful updrafts that can lift heavy rain and hail against gravity. All that motion represents energy, and it adds up quickly across a storm that may span miles and last for hours. Even before a single flash of lightning, the storm has already been doing enormous work, lifting water, moving air masses, and reshaping temperatures and pressures. When it finally unloads, it can do it with rain, wind, hail, and thunder in one overwhelming burst. Hailstones can grow in layers like onion rings of ice. A hailstone is a story of repeated journeys through the same storm. It often begins as a tiny seed, perhaps a small pellet of soft ice lifted into a cold region of the cloud by a strong updraft. There it collects supercooled droplets that freeze on contact, adding a new coat. If the updraft keeps it aloft, the stone can be carried back into wetter zones where liquid water coats it more smoothly before freezing again, creating alternating textures. Each trip upward and downward adds another layer, and those layers can reveal changes in the storm's environment, like a time capsule of temperature and moisture. Eventually, the stone becomes too heavy for the updraft to hold, and gravity wins. When it falls, it can arrive with startling force, cracking leaves, denting cars, and making streets sound like drums. Holding a hailstone is like holding a tiny cross-section of a storm's hidden machinery. Storms can spawn dozens of tornadoes from one rotating parent system. Some of the most dangerous storm days are not defined by a single tornado, but by a whole family of them. In certain setups, a large rotating storm system can persist for hours, feeding on warm inflow air while shedding tornadoes one after another along its path. The storm's rotation acts like a framework, and within it, smaller pockets of intense spin can tighten and drop toward the ground. This is how outbreaks happen, with multiple tornadoes touching down in different towns in the same afternoon or evening. For communities, this creates a special challenge, because the threat does not end after one funnel lifts. The same environment can remain primed, and new tornadoes can form quickly, sometimes wrapped in rain or hidden by darkness. Meteorologists watch for rotating signatures on radar and for patterns that suggest repeated production, so warnings can keep pace with a fast-changing situation. It is a reminder that storms can behave less like single events and more like evolving systems capable of producing surprises again and again. Hurricanes can release more heat each day than human electricity use. A hurricane is not powered by wind so much as by warm ocean water and the phase changes of water itself. As moist air rises in spiraling bands, water vapor condenses into clouds and rain, and that condensation releases hidden heat that had been stored in the vapor. The storm feeds on that warmth, using it to keep air rising, pressure dropping, and winds accelerating around the center. It is like a giant heat engine that runs day and night, taking energy that sunlight placed into the sea and turning it into motion and rain. What makes this so startling is the scale. The storm's cloud shield can stretch wider than whole countries, and the heat released by condensation happens throughout that vast churning structure. This is why a hurricane can keep going for days while appearing almost steady on satellite. Even as it constantly rebuilds itself, the ocean is the fuel tank, and evaporation is the pump that keeps it running. The tallest thunderstorms punch into the stratosphere like living towers. Some storms grow so tall that they reach a boundary where the atmosphere changes personality. In the lower layers, rising air can keep climbing if it stays warmer than its surroundings. But higher up, the temperature pattern flips, and that rising motion meets resistance. When an especially powerful updraft reaches that level, it can slam into it and spread outward, forming the familiar anvil shape, as if the storm has hit a ceiling. From the ground, these storms can look like towering mountains made of cloud, with bright sunlit edges and dark, dense bases. Inside, air is rising fast enough to carry droplets and ice high above where they started, building thick cloud tops that can cast shadows over entire landscapes. Pilots and meteorologists watch these towers carefully because their height hints at strength, and their shape can reveal how violently the air is moving within. A thunderstorm that tall is not just weather, it is architecture built from heat and moisture. Tornado winds can exceed a fast race car at full speed. A tornado is a focused spinning channel where the atmosphere concentrates motion into a tight, rotating core. It is not simply strong wind, but organized rotation that can turn fences into ribbons, lift roofs like libs, and carry debris in looping arcs through the air. What makes tornadoes so mesmerizing is the way they can be both narrow and devastating, carving a path that is fierce in one neighborhood and calm a short distance away. In some cases, winds can become fast enough to throw objects with frightening force, which is why flying debris is often the most dangerous part. Yet, tornadoes are also strange and selective. They can toss heavy items while leaving something delicate nearby, like a single tree or a small patch of grass standing by chance. Storm chasers pursue them not for thrill alone, but to measure rotation, pressure, and structure so warnings can arrive sooner. Each improved forecast can mean the difference between surprise and survival. Some storms create their own lightning factories inside swirling hail. Inside a strong thunderstorm, hail is not just ice falling from the sky. It can be part of a busy, invisible workshop where collisions build electric charge. As hailstones and smaller ice crystals tumble and crash within powerful updrafts, they swap charge in ways that separate positive and negative regions inside the cloud. Over time, the storm becomes like a giant battery with layers of charge stacked in different places, sometimes shifting as the storm evolves. When the electrical tension grows too strong for air to resist, lightning forms a sudden pathway and the stored charge discharges in a bright, branching rush. Hail makes this process more intense because it thrives in the storm's strongest updrafts, the same areas where collisions are most frequent. That is why some of the most lightning-active storms are also hail producers with chaotic cores that can sound like drum beats on rooftops. The next time you hear hail rattle, it may be the soundtrack of electricity being built overhead. Thunder is shockwave physics, not just sound rolling through clouds. Thunder does not begin as a gentle noise. It begins as a violent shove. When lightning heats air almost instantly, the air expands faster than it can smoothly flow, so it produces a shockwave, a sudden jump in pressure that pushes outward like a ring. As that shockwave travels, it stretches, bounces off clouds, buildings, and hills, and turns into the rolling, rumbling sound we recognize. Close lightning can crack sharply because the pressure change arrives more abruptly, while distant lightning often rumbles because echoes and long pathways smear the sound into a softer roll. The shape of the lightning channel matters too. A branching strike produces sound from many points at once, arriving at your ears at slightly different times, like a cord spread out across the sky. Even wind and rain can change what you hear by bending and muffling the sound. In that sense, thunder is a map made of noise telling you about distance, structure, and the hidden geometry of the lightning you may not have fully seen. The same storm can flood one town and ignite wildfires nearby. Storms are capable of producing opposites, sometimes within the same region and the same day. In one place, intense rainfall can overwhelm creeks, streets, and drains, turning low spots into rushing channels and sending muddy water into homes. A few miles away, lightning can strike dry brush or a lonely tree. And if the rain is sparse or evaporates before reaching the ground, the strike can start a fire instead of putting one out. This is especially likely when storms are high-based, with rain that falls through dry air and disappears while lightning still reaches the ground. It feels almost unfair. Water in one neighborhood and flame in another, both delivered by the same towering cloud system. These contrasts reveal how patchy storms can be, and how much depends on local humidity, wind, vegetation, and the storm structure. Weather is not always one story across a whole map. Sometimes it is many stories happening at once, stitched together by the same sky. Lightning strikes Earth millions of times each day, non-stop and global. While we sleep, while we work, while oceans roll and cities glow, lightning is constantly flashing somewhere on Earth. It clusters in stormy belts, especially where warm, moist air rises easily. And it follows seasonal patterns that shift with the sun's heating and the movement of weather systems. Over tropical land, afternoons often bring the right mix of heat and moisture, and the sky answers with towering clouds and frequent strikes. Over oceans, lightning patterns differ, shaped by sea surface temperatures and the way air flows over water. What is astonishing is how continuous this activity is, like a restless heartbeat in the atmosphere. Most strikes occur far from where any single person is watching. Yet together they form a planet-wide electrical circuit that never truly pauses. Each flash is a small reminder that air is not empty. It is a substance that can store charge, break down, and glow, linking cloud and ground in an instant. The world is quietly alive with electricity, even on nights that appear completely still. Warm ocean water is the fuel that drives hurricanes and typhoons. A tropical cyclone begins with a simple exchange, the sea offering heat and moisture to the air above it. When ocean waters are especially warm, evaporation accelerates and the lower atmosphere becomes saturated with water vapor, like invisible energy waiting to be released. As that moist air rises and cools, the vapor condenses into clouds and rain, and the released heat makes the rising air even more buoyant. That extra lift lowers pressure near the surface, which pulls in more air, which pulls in more moisture, and the engine spins faster. It is a feedback loop powered by warmth at the ocean's skin. This is why cyclones weaken over land or cooler waters, because the fuel supply is cut off or reduced. It is also why small changes in sea temperature can matter so much, influencing whether a storm stays disorganized or grows into a vast spiraling system that can reshape coastlines and rewrite maps overnight. Storm clouds separate electric charges like gigantic floating batteries. Inside a storm cloud, countless tiny collisions happen in every second, and those impacts help sort electrical charge into different regions. Ice crystals, grapple, and droplets are carried up and down by turbulent currents, bumping and scraping in ways that transfer charge like rubbing balloons on fabric, but on a massive scale. Over time, the cloud becomes electrically layered, with charge zones stacked and shifting as the storm evolves. The air between these zones acts like insulation until the electrical pressure becomes too intense, and then the cloud begins to search for a pathway. Lightning is that pathway, a sudden breakdown that turns the sky into a glowing circuit. What makes this feel so magical is that the separation is invisible while it is happening. The cloud looks peaceful from a distance, even as it is quietly organizing a powerful imbalance. Then, without warning, it corrects itself in a flash that can branch in multiple directions, lighting up the interior like a lantern. Some thunderstorms produce microbursts that slam air straight downward. Most people imagine storms as rising air, but some of the most dangerous moments come from sudden sinking. A microburst happens when a pocket of air inside a storm becomes much heavier than the air around it. Often because rain evaporates into drier air and cools it, or because melting ice chills it, that cooled air plunges toward the ground, accelerating like a falling column. When it hits the surface, it cannot keep going downward, so it spreads out in all directions as a powerful blast of wind from above. It is like dropping a stone into a pond, except the ripples are gusts that can topple trees and flip lightweight objects. For aircraft, this is especially hazardous because a plane can fly from headwind into tailwind within seconds, losing lift close to the ground. What makes microbursts eerie is their speed and compactness. They can arrive suddenly, strike hard, and fade quickly, leaving behind damage that looks like a wide splash pattern. Squall lines can stretch for hundreds of miles like moving walls. A squall line is a long connected chain of storms that organizes itself into a sweeping front. Instead of isolated heads popping up here and there, the atmosphere lines them up, often along a boundary where cooler air is pushing under warmer air. That lift triggers new storms repeatedly along the edge, so the line can persist and race forward like a living barricade. From the ground, it may look like a dark horizon that grows taller and closer, bringing a sudden shift from stillness to roaring wind. These lines can produce intense straight-line gusts, bursts of heavy rain, frequent lightning, and sometimes embedded tornadoes, all moving together as one coordinated system. They are especially dramatic at night when the flashes can strobe across an entire skyline, illuminating the line's layered structure like a moving city of cloud. A squall line's power is not just in any single cell, but in its teamwork with outflow and inflow, constantly rebuilding the advancing edge. A storm's anvil cloud spreads outward when rising air hits a ceiling. Deep inside a strong thunderstorm, air rises until it reaches a level where the atmosphere stops getting colder with height and becomes more stable. When the updraft meets that layer, it can no longer climb easily, so it spreads sideways, carrying ice crystals outward and forming the broad, flat anvil shape. This is more than a pretty silhouette. It is a sign that the storm has grown tall enough to reach a major boundary in the sky. The anvil can drift far downwind, sometimes shading areas that never see rain, and it can seed wispy cirrus clouds that linger long after the storm core collapses. Beneath it, the storm continues to churn, with rising columns feeding the top like a fountain. Sometimes the updraft is so strong that a dome-like bulge pushes above the anvil before being flattened back, a clue that the storm is still forcing its way upward. Watching an anvil is like watching a storm leave its signature across the upper atmosphere. Matus clouds look like pouches, often hanging beneath anvil. The Muse clouds are one of the sky's strangest textures, a field of rounded, drooping pockets that can make an anvil look like it has turned inside out. They often appear after a storm has done its loudest work, when the upper cloud deck begins to rearrange itself. Instead of smooth layers, the underside becomes sculpted into soft bulges, as if the cloud is slowly exhaling downward. Scientists connect mammatus to complex mixing, where different temperatures and moisture levels interact near the cloud base, creating sinking lows that stand out against surrounding air. For a viewer, they can feel uncanny, beautiful, and slightly unsettling because they hint at turbulence above without showing the storm's core. Matas does not automatically mean a tornado is coming, but it often signals that the atmosphere has been energetic and deeply layered. They are like the storm's aftermath, written in cloud shape, a reminder that the sky has depth and texture, not just color. Mesoscale convective systems can thunder through nights like traveling cities. Some storm complexes grow so large and organized that they become weather systems of their own, lasting for many hours and crossing huge distances. A mesoscale convective system is a sprawling cluster of storms that behaves like a single creature, with a broad shield of rain and cloud and active lightning-rich regions that pulse and regenerate. What makes these systems remarkable is their endurance. While a lone thunderstorm might flare and fade, these can keep going through the night, fed by steady inflow of warm, moist air and reinforced by their own outflow boundaries. On radar, they can look like massive arcs or commas, and on the ground, they can bring a long sequence of wind surges, heavy downpours, and constant, distant flashes. For people beneath them, it can feel as if the night sky has become an endless theater, with light and sound repeating in waves. They matter because they often produce major rainfall totals and widespread wind damage, not from one dramatic moment, but from persistence and scale. Supercells are rotating thunderstorms built for long life and violence. A supercell is a thunderstorm with a rotating core, and that rotation helps it stay organized in ways ordinary storms cannot. In many storms, rain falls through the updraft and chokes it off. But in a supercell, the winds are loft, or arranged so the rising air and falling rain become separated. The storm can breathe more efficiently, keeping a strong updraft while precipitation wraps around in distinctive patterns. This is why supercells can last for hours, roaming across landscapes while maintaining a coherent structure. Their rotation can tighten and intensify, supporting giant hail, intense lightning, and the conditions that sometimes lead to powerful tornadoes. For observers, supercells can look like sculpted machines with layered cloud bands, a lowered base, and features that seem almost deliberate in their symmetry. They are the storms that fill documentaries and chase footage because they display the atmosphere's physics so clearly, like a moving laboratory. Yet, they are also reminders that beauty and danger can share the same sky. Tornadoes often form where warm, moist air meets colder, drier air. Many tornado-producing days begin with a sharp contrast, a boundary where two different air masses push against each other. Warm, humid air near the surface is lighter and eager to rise, while cooler, drier air is heavier and can slide underneath like a wedge. Where they meet, the atmosphere becomes primed for lift, and lift is the spark that can build towering storms. Add strong changes in wind with height, and rotation can be tilted and stretched, helping a storm organize spinning motion into something tighter and more intense. This boundary is not always visible at ground level, but you can sometimes feel it. A sudden shift in temperature or humidity that makes the air seem different on your skin. Storms that form along such lines can intensify quickly because they are tapping into both ingredients at once. Moisture and instability, plus the structure that helps rotation develop. It is like setting the stage with opposing characters, then watching the drama unfold in the sky. The storm's updraft can lift raindrops high enough to freeze. Inside a powerful thunderstorm, gravity is not the boss, at least not right away. Rising air can surge upward fast enough to scoop up, forming raindrops, and carry them into much colder layers of the cloud. There, droplets can chill below freezing while still staying liquid for a while. A strange state called supercooled water. When these droplets finally meet an ice crystal or a tiny bit of frozen grit, they can freeze suddenly and add mass. If the updraft is strong, the growing particles are not allowed to fall. They are lifted again and again, cycling through regions of different temperature and moisture, like an elevator that never stops. This is how storms turn ordinary water into ice aloft, and why a cloud can hold a hidden blizzard inside it, even on a warm day. The next time you watch towering clouds build, imagine the unseen conveyor belts inside, hoisting water upward into a cold, glittering workshop. Lightning can travel horizontally for miles before striking ground. Lightning is often pictured as a straight bolt from cloud to earth, but many flashes are long journeys through the sky first. A strike can race sideways within a storm's charged regions, threading through cloud layers like a glowing root system, searching for an exit. This is why you can sometimes see the whole underside of a cloud light up in branching patterns, even when the ground beneath you stays dry. Eventually, a branch may find a path downward, sometimes far from the rain core that built the charge in the first place. That sideways travel matters for safety because it helps explain why lightning can strike in places that feel removed from the storm, including areas under the storm's anvil or along its edges. It also explains the eerie experience of seeing a flash without a nearby downpour. The storm is bigger than the rainfall you can see, and the electrical web inside it can stretch far beyond the curtain of rain, quietly reaching outward before it ever reaches down. Positive lightning is rarer, but often stronger and more dangerous. Not all lightning carries the same kind of punch. In many storms, the most common strikes involve negative charge moving toward the ground. But sometimes the storm's positive charge connects instead. These positive strikes tend to be less frequent, yet they are notorious because they can carry very high peak currents and can strike farther from the storm's heavy rain. That combination, stronger pulses and longer reach, makes them especially hazardous for people who think the storm has already moved away. Positive strikes are also often linked with intense storm structures, especially in mature or weakening stages when the charge arrangement can shift. They can produce exceptionally bright flashes and sharp, startling thunder that seems to hit with extra authority. They are part of why weather safety rules emphasize distance, not just rainfall. Even when the sky ahead looks lighter, the storm behind you may still be capable of reaching out with a powerful electrical handshake. It is a reminder that rarity does not mean harmlessness, and that storms keep secrets even as they fade. Dry lightning can spark major wildfires with little rainfall. Some of the most destructive fire seasons begin with storms that look generous from a distance, but offer very little water where it matters. In dry lightning setups, the air beneath the cloud base can be so warm and arid that much of the rain evaporates while falling, leaving only a few drops at the surface. Lightning still reaches the ground, and when it strikes grasses, shrubs, or forests that have been dried by heat and wind, it can start smoldering fires that may not be noticed right away. A strike can ignite a tree's interior or set leaf litter burning under a canopy, creating a hidden start that grows later as winds pick up. Sometimes, dozens of lightning ignitions can happen across remote terrain in a single evening, overwhelming firefighters before the fires even show their full size. This is one of the most unsettling storm contradictions: electricity without relief. The sky delivers the spark, but withholds the water. Understanding this helps explain why wildfire forecasts pay attention not just to heat and wind, but also to the kind of storms that might arrive and what they might leave behind. Some storms produce bolt-from-the-blue strikes far from rain. There is a particular kind of lightning that feels unfair. The strike that arrives from a sky that looks almost safe. A bolt from the blue often comes from the storm's upper regions, where charged cloud material can extend outward well beyond the rainy core. From that extended cloud, a lightning channel can form and travel outward, then suddenly drop to the ground in a place that may have sunshine, light winds, and no falling rain. People sometimes describe it as lightning from a clear sky, though the parent storm is usually visible somewhere, perhaps off to one side or hidden behind a tree. These strikes can reach surprising distances because they use the storm's sprawling top as a launch pad. They are one reason safety advice stresses that you do not need to be under a downpour to be at risk. If you can hear thunder, the electrical reach may already be close enough. The bolt's drama is in its suddenness, a reminder that a storm's true size includes parts you cannot feel, only see in silhouette. Thunder's low rumble comes from echoes and stretched-out shock waves. A coast strike can snap, but a distant one can roll like a slow drum. And that difference reveals a story about distance and space. When lightning forms, sound is generated along the entire length of the channel, not from a single point. As that sound travels outward, it reaches your ears in segments, some arriving sooner, others later, depending on how far each part of the channel is from you. Landforms and buildings can reflect the sound, adding layers, while cloud layers can bounce it back and forth like a ceiling. Over long distances, higher frequencies fade more quickly, leaving lower tones to dominate, which is why distant thunder often sounds deeper and softer. Wind can also curve sound paths, making thunder seem to come from a direction different from the lightning you witnessed. The rumble is not a single voice, but a chorus, made from many small arrivals. Each row is shaped by geometry, weather, and landscape, turning a moment of electricity into a long, wandering soundscape across the sky. Infrasonic storm sounds can travel vast distances beyond human hearing. Storms do not only speak in the thunder we can hear. They also generate deep, slow pressure waves called infrasound, tones so low that our ears do not register them as sand. These signals can travel remarkable distances, sometimes hundreds or even thousands of miles under the right atmospheric conditions, slipping through the air like a quiet message. Scientists use infrasound sensors to study storms, volcanoes, and even meteor events. Because the waves can reveal distant activity that is otherwise hidden by darkness or cloud. Infrasound from severe storms may carry information about turbulence, powerful updrafts, and large-scale storm structure. It is as if the atmosphere has a second channel of communication, one that humans do not naturally notice, yet it is always there. Thinking about this can change how a storm feels. The sky is not only flashing and rumbling, it is also pulsing with slow waves that pass through the world unnoticed, tugging gently on air pressure in a way that instruments can hear, even when we cannot. Storms can generate gravity waves that ripple through the atmosphere. When a storm pushes air upward strongly, the atmosphere can respond like a stretched fabric that has been plucked. Gravity waves are not the same as the cosmic waves you hear about in astronomy. These are ripples in air caused by buoyancy and gravity working together to restore balance after air is displaced. A strong storm can launch these waves outward and upward, creating subtle undulations that travel far from the storm itself. Sometimes they show up as bands in clouds, evenly spaced arcs that look like the sky has been brushed with a comb. Other times, they are invisible, detectable only through instruments that notice rhythmic changes in pressure or wind. These waves can influence where new clouds form, how air mixes, and even how other storms evolve nearby. It is a reminder that the atmosphere is connected, and that a thunderstorm is not just an isolated column. It can send ripples through the air around it, like a stone dropped into a pond of sky. The storm's reach is not only in rain and lightning, but in the way it can gently reshape the atmosphere at a distance. The smell after lightning comes partly from ozone and nitrogen compounds. After a nearby strike, the air can take on a sharp, clean scent that feels like the world has been freshly rinsed. Part of that smell is ozone, a molecule formed when lightning's energy splits oxygen molecules and allows them to recombine in a new arrangement. Lightning also energizes nitrogen in the air, helping create nitrogen oxides that can later become nitrates, substances that eventually wash down with rain. This chemistry is one reason storms have long been linked with a sense of renewal. The strike is not only light and sound, but also a brief moment of atmospheric transformation, changing the makeup of the air around you. The scent can be strongest near intense electrical activity, especially when winds bring those freshly formed compounds down to where you can breathe them. Of course, rain itself also stirs up soil aromas and plant oils, adding to the storm's signature perfume. Together, these scents can make a storm feel almost like a change of season, arriving in an instant. You are smelling chemistry in motion, created by a flash that lasted less than a heartbeat. Raindrops start as tiny cloud droplets, not instant falling beads. Rain begins with particles so small you would need a microscope to see them. In a cloud, water vapor condenses onto tiny airborne specks, like sea salt, dust, or smoke, forming droplets that are incredibly light. At first, these droplets float with the air and move wherever the wind and turbulence carry them. For rain to form, droplets must grow, and they do it in a few different ways, depending on the cloud. In warmer clouds, droplets can collide and merge, slowly building larger drops like a patient collecting of tiny gifts. In colder clouds, ice crystals can grow at the expense of nearby droplets, then later melt into rain as they fall. The moment a drop becomes heavy enough, it begins to descend. But even then, it may be lifted again by rising air before finally escaping. By the time rain reaches your skin, it has already lived a complicated life, shaped by invisible currents and countless encounters inside the cloud. What feels like a simple drizzle is actually the end of a long, delicate process. Raindrops' size is limited. Large drops shatter into smaller ones. Rain looks gentle, but it is also a constant physics contest between growth and breakup. As a droplet falls, it collides with smaller droplets and can grow. Yet the faster it falls, the more the air pushes back. That rushing air begins to flatten the drop, stretching it into a hamburger bun shape, then tugging it into something like a wobbling parachute. Past a certain size, the droplet becomes unstable and it tears apart into a spray of smaller drops. This is why you do not get rain that falls as giant marbles of water from the sky. The atmosphere will not let it happen for long. That shattering matters because it changes how rain sounds on leaves, how efficiently it soaks soil, and how it looks in a sunbeam when each tiny drop catches light. Even a simple shower is full of invisible splitting and reforming, millions of tiny decisions made mid-air. There is rain that evaporates before it reaches the ground. Sometimes you can watch rain falling from a cloud like pale threads, only to see it vanish before it touches the earth. That disappearing act is ver, and it happens when the air below the cloud is so dry that falling droplets evaporate on the way down. The rain is real up above, yet the ground stays dusty, and the sky seems to be playing a trick. Verizon with soft streaks, and it can also create sudden wind shifts because evaporation cools the air and makes it heavier. That cooled air can sink and spread, sending gusts across open land, kicking up dust and making a warm evening feel abruptly different. In desert regions and high plains, vega is a common sight, like weather happening at a distance. It also hints at what is going on between cloud and ground, an unseen layer of thirsty air that can steal water before it arrives. Even when it does not wet the ground, it still reshapes the air you stand in. A rain shaft can look solid, but it is countless separate drops from far away. A rain shaft can resemble a gray curtain hanging from a cloud dense enough to feel almost like a wall. But if you could slow time and step inside, you would find open space everywhere with individual drops falling through air, not a sheet of water. The illusion comes from distance and from the sheer number of drops aligned along your line of sight. Sunlight can make these shafts glow in places, or turn them merely black when the cloud is thick and the background is bright. Sometimes, a shaft seems to end sharply at a boundary, because the storm's rainfall is concentrated in one narrow corridor, while surrounding air stays dry. That sharp edge can mark where rising air is strongest, or where winds are carrying precipitation in a focused stream. Watching a rain shaft is like watching a storm reveal its plumbing, showing you exactly where the cloud is releasing its cargo and where it is holding back. Some storms create gust fronts that feel like a cool breath. There is a moment before the rain when the world changes texture. Leaves flip over. The air suddenly smells different, and a cool rush arrives, as if the storm has exhaled. That leading edge is a gust front, created when cooler, denser air from the storm spreads outward along the ground. It can race ahead of the rain, lifting warm air as it advances and making the atmosphere feel alive, like a moving boundary you can almost touch. People notice it on their skin, especially on hot days, because the temperature drop can be immediate. Birds may shift their flight, and dust may surge across a road as the front pushes through. This is not random wind. It is the storm's outflow acting like a miniature cold front, rearranging the lowest layer of the atmosphere. In some cases, it can be strong enough to break branches or topple signs even before a single drop falls. It is the storm arriving early, announcing itself with a breath. Shelf clouds mark gust fronts, rolling like a low, curved lid. A shelf cloud is one of the most dramatic storm shapes you can see with your own eyes, because it looks built like a rolling ledge sliding toward you. It forms where a gust front lifts warm, moist air ahead of the storm, forcing that air upward until it cools and condenses into cloud. The result is a low, horizontal band, often with a smooth, leading edge and a darker, turbulent underside. As it advances, it can appear to rotate or boil, not because it is a tornado, but because air is being lifted and mixed along the boundary. The shelf can stretch across much of the horizon, giving the storm a sense of scale that radar maps hint at, but cannot fully convey. For someone watching from a porch or a field, it can feel like the sky is lowering, like a lid closing softly but irresistibly. It is a visible map of airflow, showing you where the storm's cool outflow is undercutting the warm air near the surface. When a shelf cloud arrives, the storm is not just overhead, it is moving through the landscape. Storm outflow can trigger new storms by lifting warm air ahead. A storm does not always end with itself. Sometimes it creates the conditions for its own successors. As rain-cooled air spreads outward along the ground, it behaves like a moving wedge that can shove warmer air upward along its leading edge. If that warm air is humid and unstable, the lift can be enough to spark new rising towers. And those towers can grow into fresh thunderstorms. In this way, a storm can act like a match that lights other matches, each one flaring along the advancing boundary. On some summer evenings, this is why storms seem to march in lines, with new cells popping up ahead while older ones weaken behind. The outflow boundary can also bend and curve, creating pockets where lifting is especially strong. And those spots can become the birthplaces of the next big downpour. For weather watchers, outflow boundaries are fascinating because they are often invisible until clouds betray them. You might feel a breeze shift, see a subtle haze line, then notice new clouds rising as if the air has decided to stand up. The storm's influence keeps traveling even after the thunder fades. Lightning can strike the same place repeatedly in minutes. A tall object on an open landscape can become a preferred target, not because it attracts lightning like a magnet, but because it offers the shortest, easiest connection when the electric field is strong. During an active storm, conditions can reset quickly, charges rebuild, pathways in the air become favorable again, and repeated strikes can hit the same tower, tree, or ridge line in rapid succession. This is why lightning protection on skyscrapers and communication masts is designed for many hits, not a single dramatic moment. Each strike can follow a slightly different branch pattern, and the timing between them can be surprisingly short, like the storm is tapping the same spot to test it again and again. For trees, repeated strikes can be devastating, heating moisture inside and ripping bark apart. For engineers, repeated strikes are expected behavior, part of how storms discharge over time. If you have ever watched a distant tower flicker with multiple flashes in one storm, you were seeing the atmosphere finding the same convenient doorway over and over. Thunderstorms help balance Earth's electrical charge between ground and sky. Earth and the atmosphere form a planet-sized electrical system, with the ground and the upper atmosphere acting like huge conducting layers. In calm weather, a small but steady electric field exists near the ground, and a gentle current flows through the air, almost like a slow leak in an electrical system. Thunderstorms play a dramatic role in sustaining this global balance by lifting charge upward and redistributing where it resides. You can think of storms as active generators operating within an otherwise quiet electrical environment. When lightning flashes, it is not merely a local event. It is part of a larger exchange that prevents the overall system from drifting too far out of equilibrium. Scientists describe the ionosphere, high above and Earth's surface below, as two connected partners in this circuit, with storms acting as the energetic intermediaries between them. This idea is wonderfully strange because it means storms are not just weather events. They are also electrical events that connect the surface you walk on to layers of atmosphere far above airplane height. In a quiet way, storms help keep the planet's electrical bookkeeping in order. Storm clouds can carry ice crystals, liquid water, and vapor together. It is easy to imagine a cloud as one uniform thing, but many storm clouds are mixed worlds holding several phases of water at the same time. In one region, you can have tiny ice crystals glittering in frigid air. Nearby, there can be liquid droplets that remain unfrozen even below the usual freezing point, simply because they have not been triggered to freeze yet. And everywhere, water vapor weaves through, as an invisible ingredient, ready to condense or deposit onto ice. This mixed state is one reason storms can be so dynamic. Different forms of water interact, grow, and change quickly, releasing or absorbing heat as they shift between vapor, liquid, and solid. That constant switching influences buoyancy, cloud shape, and the intensity of precipitation. It also creates environments where hail can grow, where lightning becomes more likely, and where heavy rain can suddenly ramp up. A storm cloud is not a single substance floating overhead. It is a layered laboratory where water is constantly choosing what to become next, depending on temperature, motion, and chance collisions. Heavy rain can cool the air, changing a storm's own behavior. When a storm pours hard, it can reshape itself from the inside out. Falling rain drags air downward, and evaporation can cool that air even more, making it heavier and faster as it sinks. When that cooled air reaches the ground, it spreads outward and can undercut the storm's warm inflow, sometimes cutting off the very rising air that keeps the storm vigorous. This is one reason some storms collapse after a dramatic downpour, as if they used up their own support. In other situations, the spreading cool pool can push into warm air nearby and help ignite new updrafts along its edge, shifting the storm's focus and moving the action. The rain is not just a result, it is also a tool that storms use to rearrange temperature and wind near the surface. On hot days, you can feel this transformation as a sudden chill and a fresh wind that follows the heaviest burst. That callus is the storm rewriting the local atmosphere, deciding where the next lift will happen and whether the storm will fade or rebuild. The world's heaviest rainfalls can drop months of water in hours. In the right conditions, the sky can empty itself with a speed that feels impossible. Warm air can hold enormous amounts of water vapor. And when that moisture is lifted rapidly and kept rising, it can condense again and again, building thick clouds that keep refilling their own rain supply. Some of the most extreme events happen when moisture streams in steadily from a warm ocean and is forced upward by terrain or a persistent weather pattern. So the same region keeps receiving fresh, humid air like a conveyor belt. Rain can fall so hard that it turns streets into rivers, hillsides into waterfalls, and quiet creeks into roaring channels in less time than it takes to cook dinner. What makes this especially striking is that the danger is not only the total amount, but the pace. Soil cannot absorb water fast enough, drainage systems cannot keep up, and water finds every low path it can. These events are reminders that rain is not always gentle. Sometimes it is a sudden, overwhelming delivery of the atmosphere's stored moisture. Monsoon storms are seasonal shifts of wind, not just daily rain. A monsoon is often spoken of as a rainy season, but its true heart is a giant change in wind direction, driven by heating differences between land and sea. As land warms more strongly than nearby oceans, air rises over the continent, and that rising motion draws in moist air from over the water. Over weeks, the pattern becomes reliable, like a seasonal breath, bringing moisture inland and feeding repeated storm development. The rain can arrive in bursts, with dramatic downpours and then breaks of sun. Because monsoons are not a single storm, but a shifting system that creates many opportunities for storms to form. In places influenced by monsoons, daily life adapts to this rhythm. Crops, rivers, reservoirs, and even architecture are shaped by the expectation that the sky will eventually open. Yet, monsoons can also be delicate.
Their timing and strength can vary, and small changes can mean drought in one year or flooding in another.
Thinking of a monsoon as wind first and rain second makes it feel even more like a living, seasonal machine. Oraphic storms form when mountains force air to climb and cool. Mountains can make weather without ever moving, simply by standing in the path of wind. When moist air flows toward a mountain range, it has only a few options, and one of them is to rise. As it climbs, the air expands in the lower pressure and cools. And cooling encourages water vapor to condense into cloud. If the lift is steady, clouds thicken and precipitation begins, often focused along the windward slopes where the air is being forced upward mostly. This is why some mountain valleys can be lush, while nearby plains are much drier, and why hikers can walk from sunshine into fog and rain in a short distance. On the other side of the range, the descending air warms and dries, creating a rain shadow where clear skies are more common. In a sense, the mountain is a giant weather gate, squeezing moisture out of the air on one side and guarding dryness on the other. It turns geography into atmosphere, shaping storms with stone and height. Lake-effect snowstorms can dump huge snow from relatively small lakes. A lake-effect snowstorm begins with cold air sweeping over a comparatively warmer lake surface. The lake adds heat and moisture to the air above it, and that warmed, moistened air becomes more buoyant and rises as it travels downwind. As it rises, it cools and clouds form in long bands that can organize into narrow corridors of heavy snowfall. The result can be astonishingly localized. One town might be buried under deep snow, while a nearby area remains almost untouched, simply because the snow band is narrow and persistent. These bands can keep dumping snow hour after hour if the wind direction stays steady, effectively aiming a snow machine at the same place. The snow can be fluffy or dense depending on temperature, but the intensity can be startling, reducing visibility and quickly building drifts. Lake-effect storms show how water bodies can act like fuel sources even in winter, feeding clouds with moisture that becomes snow. It is the lake lending its warmth to the sky, only to return it as snowfall on the land. Blizzards are defined by wind and visibility, not snowfall amount. The word blizzard makes people think of huge snowfall totals, but the defining features are wind-driven chaos and dangerously low visibility. You can have a true blizzard even with little new snow falling, if strong winds pick up existing snow and hurl it through the air like white sand. The result is a world where distance disappears, where familiar landmarks fade, and where you can lose your sense of direction only a few steps from shelter. This is why blizzards can be so deadly. The cold is intense, the wind steals heat quickly from skin, and the blowing snow makes travel and rescue difficult. Roads can vanish under drifting, and vehicles can become trapped in minutes. A blizzard is not only about what falls from the sky, it is about what the wind does with what is already there, turning the landscape into a shifting, moving veil. It can feel like the atmosphere is sanding the world down to pure whiteness, reducing everything to wind, cold, and disorientation. Understanding the definition helps explain why warnings focus on visibility and wind, not just how many inches might accumulate. Thundersnow happens when snowstorms produce lightning and booming thunder.
Thunder snow is one of the rarest and most surreal storm experiences because it combines the hush of snow with the sudden violence of thunder. For lightning to occur in a snowstorm, the storm must have strong vertical motion and enough mixing of ice particles to build electrical charge, much like a summer thunderstorm, but in a colder setting. When lightning flashes inside a thick snowfall, the light can diffuse through the flakes and cloud, creating a soft, eerie glow that makes the world look briefly blue-white. Then comes the thunder, often muffled by the snowpack and the heavy air, sounding closer and deeper than you expect. Thunder tends to occur in intense winter systems, sometimes near coastlines or within strong snow bands where the atmosphere is unusually energetic. It can also appear in lake effect situations when rising motion is vigorous. The contrast is what makes it unforgettable. Snow usually suggests silence, but thunder snow reminds you that winter can be electrically alive. It is the sky finding a way to crackle, even when the world below is wrapped in cold. Ice storms coat landscapes with glaze from freezing rain. An ice storm can transform the world into a glass sculpture, beautiful and dangerous at the same time. It often begins with a layer of warm air sitting above a shallow layer of cold air near the ground. Snow forms higher up, melts into rain while passing through the warm layer, then becomes supercooled as it falls into the colder air below. When those supercooled droplets strike trees, power lines, roads, and railings, they freeze instantly into a smooth, clear coating. That glaze can build quickly, adding weight to every branch and wire. Trees that have stood for decades can crack under the load, and power infrastructure can sag or snap. Roads become slick in a way that is hard to see because the ice can be nearly transparent. The soundscape changes too. Branches crack, ice clinks in the wind, and the world feels fragile. Unlike fluffy snow, glaze ice is dense and heavy, and it clings to surfaces with determination. Ice storms reveal how small changes in temperature layers can flip winter weather from pretty to paralyzing. Freezing rain forms when droplets stay liquid below freezing and flash freeze. It feels counterintuitive, but water can remain liquid even when the air is below the freezing point if it lacks a trigger to crystallize. In the atmosphere, droplets can become supercooled, chilled below freezing while still fluid, like tiny suspended beads waiting for a cue. When these droplets hit a surface, the impact provides that cue, and the water freezes almost instantly, spreading into a thin sheet of ice that conforms to whatever it touches. This is why freezing rain is so dangerous. It does not bounce away like sleet or pile up like snow. It creates a smooth, continuous layer that turns sidewalks into skating rinks and roads into traps. On trees and lines, the ice builds outward, thickening with each wave of rain. The process also explains why freezing rain can happen even when you do not see snowflakes at all. The cloud above is producing precipitation, but the temperature layers beneath it decide the final form. When those layers align just right, the result is a storm that paints everything in clear ice, quietly and relentlessly. Sleet is refrozen raindrops, tiny ice pellets that bounce. Sleet forms when raindrops begin as liquid, but then fall through a deeper layer of freezing air that gives them time to turn solid before reaching the ground. Instead of coating surfaces with glaze, these refrozen drops arrive as small pellets that can bounce and rattle, sounding like handfuls of rice thrown onto windows. Because sleet is solid, it builds up differently than snow. It can collect in crunchy layers and combine with snow to form dense, compacted surfaces that feel heavy and slick. Sleet also offers a clue about what is happening in the atmosphere above you. It points to a warm layer aloft that melted snow into rain, paired with a colder layer below that quickly refroze it. In this way, sleet acts as a message from the sky's hidden temperature structure. It can make driving especially dangerous because the pellets can roll beneath tires like tiny ball bearings. Yet it often lacks the dramatic look of a heavy snowfall. It is winter weather with a quiet edge, arriving as bouncing grains that signal layered air and difficult transitions. Grapple is soft hail like little icy beads of foam. Grapple looks like small white pellets that resemble tiny popcorn pieces or foam beads. And it forms when snowflakes are coated by supercooled droplets that freeze onto them. Unlike sleek hailstones, grapple is often soft and crumbly because the coating traps air and creates a frosty texture. It can fall in sudden bursts, peppering the ground and rooftops with a gentle rattle, then melting away quickly if temperatures are mild. Because grapple forms in clouds where supercooled water and ice crystals coexist, it is a sign of lively cloud physics, where different phases of water are mixing and colliding. On mountain slopes, prowl can be especially important because it can behave like tiny ball bearings on snow surfaces, creating slippery layers that sometimes contribute to avalanche conditions later. For anyone watching the sky, grapple is a delightful surprise because it does not fit the simple categories of rain, snow, or hail. It is a middle form, a soft ice pellet born from snowflakes that were suddenly dressed in frozen droplets. It reminds you that the atmosphere has many ways to turn water into something new. Tropical cyclones have different names, but the physics is the same. Around the world, people use different words for the same kind of giant spinning storm, depending on where it forms. In one ocean basin, it is called a hurricane. In another, a typhoon, and in others, it may simply be called a cyclone. The naming can make them feel like different creatures, but the basic recipe is shared. Warm ocean water feeds moisture into the air. Rising motion builds tall clouds, and the spinning earth helps organize the flow into a rotating system. As air spirals inward near the surface, it speeds up, and the storm becomes a vast machine that converts heat and water vapor into wind and rain. What changes from place to place is the environment around the storm, the steering winds, the nearby land shapes, and the local ocean patterns that can help a system grow or tear it apart. Knowing the shared physics helps you understand why storms in different oceans can still look strikingly similar from space, like cousins wearing different regional names. An eye forms when a cyclone's core becomes calm and sinking. At the heart of many powerful cyclones is a surprising feature, a calm center that can feel almost peaceful compared to the chaos around it. This happens when the storm's strongest rising motion wraps into a ring, leaving the very center dominated by sinking air. Sinking air warms as it compresses, which discourages cloud formation, so the middle can clear out into a circular window. From above, it looks like the storm is staring back, a quiet pupil surrounded by a swirling iris. Inside that calm, winds can drop dramatically, skies can brighten, and in some cases, stars can appear at night. Yet, the calm is a trap for the unprepared, because the most violent part of the storm is not far away. The eye is bounded by towering clouds and fierce winds, and when the storm moves, that boundary can sweep over a location quickly. The eye's existence is a sign of organization and strength, like a spinning top that has found balance. It is the storm's still point, created not by gentleness, but by intense structure. The eye wall holds a storm's fiercest winds and heaviest rain. If the eye is the storm's quiet center, the eye wall is its roaring fortress. This is a ring of deep thunderstorms wrapped tightly around the core,
where air rises violently and the pressure difference is steep. Steeper pressure gradients drive faster winds, so the eye wall often contains the strongest sustained winds in the entire cyclone. It is also where rain can fall in blinding sheets, and where the atmosphere can feel like it is being run out. The clouds here can climb to extraordinary heights, and the turbulence can be severe, making it one of the most challenging regions for any aircraft that studies storms.
For people on the ground, the eye wall's passage is often the defining experience. The hours when roofs strain, trees twist, and waves surge. What makes it so gripping is the sharp contrast. Conditions can worsen rapidly as the eye wall arrives, then ease if the eye passes overhead, only to become fierce again as the far side of the eye wall returns. It is the storm's main engine room, concentrated into a moving ring. Eye wall replacement can weaken a hurricane, then strengthen it again. Sometimes a cyclone does something that feels like a magician's trick, tearing down its own strongest ring and building a new one. In an eye wall replacement cycle, a second ring of thunderstorms forms outside the original eye wall. This outer ring can gradually tighten and begin to starve the inner ring of moisture and inflow, causing the inner eye wall to collapse. During this transition, peak winds often decrease because the strongest circulation is reorganizing. But the story does not always end with weakening. Once the outer eye wall becomes dominant, the storm can intensify again, sometimes with a larger area of strong winds than before. This matters because a storm can become broader even as its maximum wind changes, altering where the most damaging conditions occur. From satellite imagery, these cycles can appear as concentric rings, like ripples around the eye. For forecasters, they are a challenge because they can shift intensity and structure on a timescale of hours. For anyone in the path, they are a reminder that storms evolve and that a temporary lull does not always mean the danger has passed. Storm surge is ocean water pushed ashore, not simply high waves. Storm surge is often misunderstood as just big surf, but it is more like the sea itself being lifted and shoved onto land. Powerful winds push water toward the coast, and low pressure in the storm's center allows the ocean surface to rise further, like the water bulging upward under a lighter weight of air. When that elevated water reaches shallow coastal shelves, it can pile up even more, flooding areas that may be far from the immediate shoreline. The most dangerous surge often arrives with a coastline shape and seafloor contour funnel water into bays, estuaries, and river mouths, turning geography into an amplifier. Waves ride on top of the surge, adding force that can break structures and erode dunes. But the surge is the part that brings the ocean inland and keeps it there. It can turn streets into channels and trap people in places they thought were safe. What makes surge so frightening is that it can rise steadily and silently, especially at night. And its depth and speed can be hard to judge until it is already moving through neighborhoods. Hurricanes can grow larger over pooler water, even while weakening. It seems logical to assume a hurricane must shrink if it weakens. Yet storms can expand even as their peak winds decrease. A cyclone size is tied to its broader wind field and the way it interacts with the surrounding atmosphere, not only to the warmest water beneath its core. As a storm moves into less favorable conditions, its central engine may lose intensity, but the circulation can spread outward, with winds and rain bands covering a wider area. This can happen when the storm begins to draw energy from temperature contrasts in the environment, or when its structure reorganizes after internal changes. For people, this is important because a larger storm can deliver widespread coastal surge, long periods of tropical storm force winds, and heavy rain far from the center. Even if the strongest winds are not extreme as before,
it changes the map of impact.
A compact, intense cyclone can be devastating near its core, while a broader, somewhat weaker one can create hazards across a much bigger region. Size is its own kind of power, and storms do not always shrink politely when conditions deteriorate. A storm's size can matter more than its peak wind speed. When people talk about storms, they often focus on the single strongest wind number. But the footprint of the storm can shape the real experience on the ground. A larger cyclone pushes on the ocean over a wider area, which can build more extensive storm surge and higher, longer-lasting swells. It can also bring heavy rain bands far inland and keep windy conditions going for many hours, increasing tree damage and power outages through sheer duration. Even outside the core, broad wind fields can drive waves, stress structures, and complicate evacuation because impacts are spread across multiple coastlines or states at once.
Meanwhile, a smaller storm with higher peak winds may concentrate its worst effects into a narrower corridor. Both can be dangerous, but in different ways. This is why forecasters and emergency planners pay attention to wind radii, storm structure, and forward speed, not just the headline category. The storm is not a single number. It is an area of influence, and sometimes the most disruptive storms are the ones that simply cover more of the world with their reach. The Coriolis effect helps storms rotate, but it does not create wind. Earth's rotation changes how moving air appears to curve across the globe. A tendency known as the Coriolis effect. It does not start the wind in the first place. Wind begins because air flows from higher pressure toward lower pressure, driven by uneven heating and the need for balance. Coriolis then bends that flow, shaping straightened motion into spirals around low-pressure centers.
This bending is why cyclones rotate in opposite directions in different hemispheres, and why large weather systems organize into sweeping patterns rather than simply rushing inward like water down a drain. The key is scale. Coriolis becomes more influential over larger distances and longer times, which is why tiny whirlwinds in a parking lot do not depend on it, while planet-sized weather systems do. Understanding this makes storms feel even more elegant. The storm is not spinning because the air wants to spin. It is spinning because the planet itself is rotating under the moving air, gently steering it into curves that build the storm's signature swirl. Cyclones rarely form near the equator because rotation is too weak. Near the equator, something subtle but crucial is missing for tropical cyclone birth. Enough Coriolis influence to help organize rotation. The Coriolis effect is strongest toward the poles and weakest at the equator. So air near the equator does not get bent into a strong spiral as easily. Without that turning, thunderstorms may still blossom over warm seas, but they struggle to consolidate into a single, rotating core with a defined center. The result is often a cluster of storms that can dump heavy rain yet fails to become a true cycle. This is why most tropical cyclones form several degrees away from the equator, where the turning influence is strong enough to help a low-pressure area spin up and maintain its structure. It is a beautiful example of how a global property, the rotation of Earth, sets invisible boundaries on what kinds of storms can exist where. The equator is not calmer because it is protected by magic. It is calmer in this specific way because the geometry of rotation changes with latitude, and storms must follow that rule. Some tropical systems rapidly intensify in a single day. Rapid intensification is one of the most dramatic transformations in weather. When a tropical system strengthens far faster than most people expect, a storm that seemed manageable in the morning can become far more dangerous by the next sunrise, because the environment suddenly lines up in its favor. Very warm ocean water, high humidity,
and low wind shear can allow the storm's core to tighten with pressure dropping and winds accelerating as the cyclone becomes more efficient at pulling in and lifting air. Once the inner circulation organizes, the storm can build a feedback loop where stronger winds draw in more moisture, which fuels deeper convection, which further strengthens the winds. Forecasters watch for signs like improving symmetry, strengthening inner rain bands, and falling central pressure, because rapid changes can shrink preparation time. For coastal communities, this is one of the most stressful storm behaviors, because it challenges normal expectations of gradual development. Rapid intensification is a reminder that storms are not always slow-building threats. Under the right conditions, the atmosphere can shift gears quickly, and a system can leap from ordinary to extraordinary in less than a day. Atmospheric rivers are narrow moisture highways that feed extreme storms. Imagine a long, invisible ribbon of damp air stretching across an ocean, quietly transporting moisture like a conveyor belt in the sky. An atmospheric river is a narrow, concentrated band of water vapor that can stretch for thousands of miles while remaining only a few hundred miles across. Under calm conditions, it is simply moisture flowing through the sky. But when it reaches land and is lifted by mountains or weather fronts, that vapor is forced upward, condensing into dense clouds and heavy precipitation. The outcome can be prolonged periods of intense rain or deep mountain snowfall, delivered with a persistence that feels unyielding. What makes atmospheric rivers especially intriguing is that they are not storms on their own. They function as fuel channels that storms draw from. One river can supply multiple systems in succession, keeping waterways swollen and slopes saturated. From space, you might see a pale plume aimed at a coastline, like a soft arrow. On the ground, you experience it as a storm that seems to have an endless supply, because, in a sense, it does. The sky is importing water from far away. A single atmospheric river can carry more water than major rivers. It is hard to grasp water vapor as something that can be measured and compared, because you cannot hold it in your hands. Yet the amount of moisture moving through an atmospheric river can be enormous, enough that the total transport rivals or exceeds the flow of some of the world's great rivers. Instead of rushing through a channel of rock, it flows through a channel of wind, guided by pressure patterns and shaped by temperature. This comparison matters because it hints at how quickly landscapes can change when that moisture finally falls out as rain or snow. A river on the ground is limited by its banks. A river in the sky can be steered and intensified by weather systems. And when it arrives at a mountain range, the air is forced upward and the moisture can unload efficiently. Suddenly, the air that seemed empty becomes a source of flooding creeks, roaring waterfalls, and snowpack that builds in a single storm cycle. Thinking of it as a river you cannot see helps the mind accept the scale. The atmosphere is capable of moving water in quantities that feel almost geological. Narrurs can combine ocean moisture with cold air for huge snow. A nor'aster is a coastal storm that draws its power from contrast. Cold air spills down from the continent while the ocean remains relatively warmer, offering moisture and heat to the atmosphere just offshore. As winds wrap around a developing low-pressure system, they can pull that ocean moisture into the cold air, creating thick cloud bands that produce heavy precipitation. If temperatures are right, that precipitation falls as snow, sometimes in dense bursts that pile up faster than plows can keep up. The name comes from the strong winds that blowing from the northeast along the coast, driving waves, throwing spray, and adding coastal hazards on top of inland snow. What makes Nor'razors memorable is their ability to linger and to wrap moisture back toward land again and again, creating long-duration storms rather than quick hits. They can produce sharp gradients too, with heavy snow a short distance inland and rain closer to the coast, depending on the storm track. A nor'aster is a reminder that winter storms can be ocean-fed, not just cold-driven. The sea helps ride the snowfall. Bomb cyclones deepen rapidly, making winds intensify fast.
Some mid-latitude storms strengthen with a speed that feels like a sudden drop into a steep valley. A bomb cyclone is a storm whose central pressure falls very quickly, a sign that the system is intensifying rapidly. When pressure drops fast, the pressure difference over distance becomes stronger, and that can accelerate winds, sometimes producing conditions that rival tropical storms in certain regions. These storms often thrive where warm and cold air masses clash sharply, and where upper-level winds help remove air from the storm's top, encouraging more air to rise from below. The ocean can add extra energy as well, especially in winter, when cold air sweeping over warmer water creates strong instability and moisture supply. For people, the effect can be dramatic. A forecast that seemed manageable can turn into a night of roaring wind, pounding surf, and rapid changes in weather. Bomb cyclones can also produce heavy snow in their colder sectors and intense rain in warmer sectors, depending on where you are relative to the storm center. They are not a different species of storm so much as a storm that has found a way to grow quickly, like a spinning system suddenly tightening its grip. Mid-latitude storms feed on temperature contrasts like engines of imbalance. Away from the tropics, many large storms are powered by the difference between warm air and cold air. The atmosphere trying to smooth out an imbalance. When warm air lies next to colder air, nature wants to mix them, because that contrast represents stored energy. A mid-latitude cyclone is one way the atmosphere does the mixing, wrapping warm and cold air around the low-pressure center in swirling bands. Warm air is lifted, cooled, and turned into cloud and precipitation, while cold air sweeps in behind, often bringing clearer skies but strong winds. Over time, the storm can build fronts, sharp boundaries you can sometimes feel as a sudden shift in temperature, wind, or humidity. These storms are the architects of many familiar weather changes, the systems that bring springtime squalls, autumn gales, and winter blizzards. They can also stretch enormous distances, affecting several states or countries at once. Thinking of them as engines helps. They are not random. They are the atmosphere doing work to reduce contrast, turning uneven heating into organized motion, and converting that motion into wind, waves, clouds, and rain. The jet stream steers many storms like a high-altitude conveyor belt. Far above the ground, narrow bands of strong winds race around the planet, and these fast flows help guide where storms go. The jet stream forms along strong temperature boundaries high in the atmosphere, and it can behave like a winding river of air with bends that deepen and shift over days. Storms tend to form and intensify near these jets because the wind patterns aloft can encourage rising motion below. And once storms exist, the jet can act like a steering current. When the jet dips south,
Colder air can spill downward, and storm tracks can follow that dip. When it shifts north, warmer patterns may expand. For forecasters, the jet is a key clue for where a storm might travel and how quickly it might move. For a viewer, it is fascinating because it reveals that weather is not only a surface story. The clouds you see are often riding underneath a high-speed guide rail you never feel directly. The jet ream can also make storms race or slow, depending on how straight or wavy it becomes. It is the invisible hand that often nudges storms across maps. Blocking patterns can trap storms, causing long, stubborn rain events. Sometimes the atmosphere settles into a pattern that refuses to budge, like furniture pushed into the path of moving air.
A blocking pattern is a large-scale setup that slows or stalls the usual west to east progress of weather systems. When this happens, storms can linger over the same region or repeatedly pass over it along nearly the same track. The result can be long stretches of rain day after day. Not necessarily violent in any single hour, but relentless in accumulation. Rivers rise, soils saturate, and the risk of landslides and flooding increases because the ground never gets a break. Blocking can also lock in heat waves, but when it locks in wet weather, it can feel as if the sky has forgotten how to change. Forecasts become less about a single storm and more about persistence, about how long the pattern will hold before it finally loosens. For meteorologists, blocks are fascinating because they are expressions of big atmospheric waves that can stall. For ordinary life, they are exhausting because they turn weather into a stuck record. The storm is not always dramatic. Sometimes it is simply unwilling to leave. Thunderstorms often form along boundaries you cannot see at ground level. A calm afternoon can hide sharp, invisible lines in the atmosphere. Boundaries where temperature, humidity, or wind direction change over a relatively short distance. Along these lines, air is nudged upward, and that gentle lift can be the spark that turns ordinary warmth into towering clouds. A sea breeze front can push inland from the coast, meeting hotter air and forcing it to rise. An old outflow boundary from yesterday's storms can linger like a faint seam, ready to reawaken storm development when the sun heats the ground again. Even subtle wind shifts can create convergence, where air piles up and has nowhere to go but up. To a person on the ground, the day may feel uniform, yet the sky knows better. Then, seemingly out of nowhere, one cloud grows taller than the rest, and within an hour, it becomes a thunderstorm. This is one of the most captivating things about storms: their ability to begin at the edges of things you cannot see. The boundary is the stage, and the storm is the sudden actor, appearing where the atmosphere quietly arranged a lift. Storm forecasting improved when satellites began watching cloud tops globally. Before satellites, vast stretches of ocean and remote land could hide developing storms from human eyes. Ships and scattered stations offered clues, but the atmosphere could build systems far from observers. Satellites changed that by giving meteorologists a global view, letting them watch cloud patterns evolve in real time. From above, you can see the spiral of a forming cyclone, the cold, high cloud tops of powerful thunderstorms, and the sweeping arcs of fronts stretching across continents. You can also track how storms breathe, pulsing with new bursts of convection or collapsing and reorganizing. Different satellite sensors reveal different secrets. Infrared imagery highlights cold cloud tops at night as well as day. Water vapor imagery shows moisture patterns and upper-level dynamics that shape storm development.
This bird's-eye perspective has improved early warnings, especially for storms forming over open water, where communities might otherwise have less time to prepare. It also changes how storms feel to us culturally. We now see weather as a moving set of patterns on a living planet, not just what happens outside the window. Satellites turn storms into something we can watch as they are born. Doppler radar reveals rotation inside storms before tornadoes appear. A storm can look ordinary from the outside while hiding organized motion within. And Doppler radar helps reveal that hidden motion by measuring how precipitation is moving toward or away from the radar site. When winds inside a storm begin to rotate strongly, radar can detect that signature even before a funnel forms. This has transformed tornado warnings from purely reactive to more anticipatory, giving communities precious minutes to take shelter. Radar can also show where rain is wrapping around a rotating core, where hail may be present, and where strong winds are descending. For storm scientists, it is like having a stethoscope pressed against the atmosphere, listening to the storm's internal circulation. For the public, it has made severe weather less mysterious and more trackable. You may see maps with colored velocity patterns, and those colors represent real air motion, not just clouds. It is one of the most powerful ideas in modern forecasting that you can sense wind indirectly by watching the movement of raindrops and hail. The storm reveals itself through what it carries, and radar turns that into an early glimpse of what might come next. Hulk echoes on radar can hint at tornado-producing supercells. On a radar screen, most rain looks like blobs and bands, but occasionally, a storm draws a shape that looks like a curved hook. That hook forms when precipitation wraps around the storm's rotating core, like water curling around a spinning drain. And it can be a warning sign that the storm is organized in a way that sometimes produces tornadoes. The hook is not the tornado itself. It is a clue about structure, showing that air is rotating strongly enough to bend the storm's rain pattern into a recognizable signature. What makes this so powerful is the idea that you can read a storm's internal motion from the way it arranges its own rainfall. Meteorologists watch hooks alongside other radar clues, looking for tightening rotation and changes over time, because storms evolve quickly. For viewers at home, it can feel like a secret language, the atmosphere writing a hint in the placement of rain. When a hook appears, it is as if the storm is showing its hand, revealing that something more focused and potentially dangerous may be forming within. Lightning mapping networks can track a storm's electrical heartbeat. A thunderstorm is not just wind and rain. It is a living electrical machine that flickers constantly inside its clouds. Lightning mapping networks detect radio signals from lightning and turn them into maps of where flashes are occurring, sometimes with incredible detail. Instead of seeing a single bolt, scientists can watch the storm's electrical activity spread, cluster, and change shape. Almost like watching pulses move through a nervous system. This matters because lightning often increases when storms intensify, and sudden changes in lightning patterns can signal shifts in the storm's internal structure. Some storms light up with frequent in-cloud flashes long before the most hazardous weather begins, offering an early hint that strong updrafts are building. Lightning maps can also help track storms at night or in remote areas where visual observation is limited. There is something mesmerizing about the concept. A storm has a kind of electrical rhythm, and these networks let us listen to it with instruments. They show that the sky is not only moving. It is communicating through bursts of charge, a flickering heartbeat hidden inside cloud walls. Storms can produce sprites high above clouds, glowing red tendrils. Far above the familiar lightning zone in the thin air near the edge of space, storms can trigger brief flashes of light called sprites. They appear above the storm top, often as reddish branching shapes that last only a fraction of a second, like ghostly jellyfish or upside-down trees. Sprites are not ordinary lightning bolts. They are electrical discharges that occur high in the atmosphere, sparked by powerful lightning activity below that changes the electric field above the storm. For a long time, sprites were rumored by pilots and dismissed as legends because they were so fleeting and hard to photograph. Once cameras finally captured them, they opened a new layer of storm wonder, a reminder that storms connect the lower atmosphere to much higher regions than we usually imagine. Sprites also reveal how electricity can behave differently in thin air, spreading into large, delicate shapes instead of tight channels. Knowing they exist makes storms feel taller. The storm is not only reaching upward with cloud towers, it is also influencing the sky above the tone top, lighting a hidden theater far overhead. Blue jets shoot upward from storm tops toward the upper atmosphere. A blue jet is one of the most dramatic things a thunderstorm can do without most people ever noticing. Instead of discharging toward the ground, a jet can launch upward from the storm's top, a narrow bluish cone of light that shoots into thinner air above. These events are rare and brief, often captured by aircraft crews or sensitive cameras rather than casual observers. The blue color is linked to the way excited molecules emit light at those wavelengths in the upper atmosphere, and the shape suggests a focused channel that expands as it rises. Blue jets highlight a startling idea. Storm electricity does not always choose the shortest path to the ground. Sometimes it seeks a path upward toward regions where the air is less dense. And electrical breakdown can take different forms. The jets can reach tremendous heights compared to a typical lightning channel, bridging the storm's top with atmospheric layers that feel almost out of reach. They make thunderstorms feel like portals, not only between cloud and ground, but between the lower atmosphere and the space above it. If sprites resemble delicate artwork painted in the upper sky, blue jets feel like a storm hurling a spear of light upward into the darkness. Elves are vast, faint rings of light, produced by powerful lightning pulses. Elves are among the most astonishing storm phenomena because of their sheer scale. They appear as enormous, expanding rings of dim glow that can spread across the upper atmosphere almost instantly, triggered by the electromagnetic pulse of intense lightning below. Unlike sprites, which often form branching tendrils, an elf looks more like a luminous ripple, a brief circular wave that rapidly grows and then disappears, often in less than the time it takes to blink. Their faintness makes them difficult to see with the naked eye, but sensitive cameras and satellites can detect them as they spread across high-altitude layers. The ring shape comes from the way the pulse interacts with the ionized region above, creating a rapidly expanding disturbance. It is like tossing a stone into an invisible pond, except the pond is the upper atmosphere and the ripple is light. Elves remind us that lightning is not only a current in a channel, it is also a powerful burst of electromagnetic energy that can affect regions far above the cloud tops. Storms, in other words, can paint the sky in huge, quick strokes that most of us never notice, happening quietly above the spectacle we already find impressive. Some storms create rare ball lightning reports, still not fully explained. Every so often, people describe something that sounds like science fiction. A glowing sphere of light that appears during a storm, drifts or hovers briefly, and then fades or vanishes suddenly. These reports are often called ball lightning, and they remain one of the most puzzling storm phenomena because they are difficult to capture clearly and reproduce in controlled conditions. Some accounts describe balls that move through open windows, float along the ground, or appear near the point of a lightning strike. Because storms are chaotic and dangerous, careful measurements are rare, which leaves room for uncertainty and debate about what exactly people are seeing. Scientists have proposed ideas ranging from glowing plasma sustained by unusual electrical conditions to chemical reactions triggered by intense energy. It is possible that different mechanisms could produce similar-looking effects, adding to the mystery. What makes ball lightning so captivating is that it sits at the boundary between everyday experience and unresolved science. It reminds us that even with satellites and radar, storms still surprise us. The sky can produce events that leave eyewitnesses searching for words and researchers searching for explanations. Thunder can be silent if lightning is far enough away. It feels strange, but you can sometimes see lightning without hearing anything at all, even when the flash seems bright and clear. This happens because light travels so quickly that distance barely matters, while sound moves much more slowly and is easily weakened over long paths. If the lightning is far enough away, the thunder may arrive too faint to hear, or it may be absorbed and scattered by the atmosphere and the landscape before it reaches you. Wind direction can make this effect stronger, carrying sound away from you like a moving conveyor. Layers in the atmosphere can also bend sound upward, letting it skip over the ground. The result is silent lightning, often seen on warm nights at a distance where the horizon flickers like a quiet strobe behind clouds. People sometimes call it heat lightning, but the flashes are usually from real storms far away. There is something hypnotic about watching the sky light up without any sound, as if the storm is performing behind glass. It is a reminder that your senses give you only part of the story, and that storms can be present beyond your hearing. Lightning can strike through volcanic ash clouds during eruptions. When a volcano erupts, it can create its own storm-like environment, hurling ash, gas, and rock fragments into the sky. Inside that chaotic plume, particles collide and rub, building electrical charge much like ice particles do inside a thunderstorm. The result can be lightning crackling within the ash cloud, bright forks illuminating billowing gray like a lantern inside smoke. This volcanic lightning is both beautiful and unsettling because it combines two powerful forces at once: fire from the earth and electricity in the air. The flashes can help scientists estimate plume height and intensity. And in some cases, lightning detection systems can even contribute to eruption monitoring when visibility is poor. For viewers, it expands the idea of what lightning belongs to. It is not only a product of rain clouds. It can arise wherever particles and turbulence create strong charge separation, even in a plume that contains little water. Volcanic lightning makes the sky look alive with sparks above an eruption, as if the atmosphere is reacting to the violence below by snapping and flashing in response. It is one of the clearest reminders that electricity is a universal tool of nature, not limited to one kind of storm. Dust storms can make their own lightning from colliding grains. A dust storm can look like a rolling wall of earth, but within it, countless sand and dust grains are colliding and scraping in the wind. Those collisions can transfer charge, leaving some particles more positive and others more negative. When the storm becomes dense and turbulent enough, the charge separation can build into electric fields strong enough to produce sparks and even lightning-like discharges. This is especially intriguing because there may be little or no rain involved at all.
The storm is dry, yet electrical. In dusty environments, people have reported glowing discharges and crackling sensations. And researchers study these effects because they may influence how dust storms behave and how particles clump or disperse. Dust electrification also has a planetary twist. Similar processes may occur in dust storms on Mars, with a thin atmosphere and abundant dust could allow electric effects that shape both weather and exploration risks. Thinking of dust as electrically active changes the picture. The storm is not just moving dirt, it is building and releasing charge as it grinds the landscape into the air, turning friction into electricity in a swirling brown sky. Snowstorms can build static charge, leading to surprising shocks. Winter storms can feel quiet, but they can also be surprisingly electric. Blowing snow and ice crystals can rub against each other and against surfaces, transferring charge and building static.
In much the same way, dry air makes static cling more noticeable. In very cold, dry conditions, charge can accumulate on clothing, hair, and metal objects, and then discharge as a sudden snap when you touch a doorknob or a car handle. During certain intense snow events, especially with strong winds, this electrification can become more pronounced, and people may notice crackling sounds, tiny sparks, or a persistent prickly feeling. The atmosphere's dryness matters because moisture usually helps charge leak away. But cold air often holds little water vapor, letting static build. This is not the same as lightning, yet it is part of the same family of phenomena: charge, separation, and discharge. It adds a hidden layer to winter weather, a reminder that snow is not only frozen water, it can be a moving field of tiny crystals colliding and charging as they fly. Even a storm that looks soft and white can have a sharp electrical edge. A haboob is a towering wall of dust driven by storm outflow. A haboob can look like the horizon has decided to stand up and walk toward you. It begins when a thunderstorm's rain-cooled air collapses downward and spreads across the ground, pushing outward like a fast-moving wedge. In dry landscapes, that surge of wind grabs loose soil and dust, lifting it into a dense, rolling front that can rise hundreds or even thousands of feet. From a distance, it resembles a brown tidal wave with a crisp leading edge and a boiling, turbulent top. As it arrives, daylight can dim quickly. Visibility can drop to near zero, and the air can feel suddenly gritty and thick. People caught in one describe an eerie hush and a muffled world, as if the storm has wrapped everything in cloth. Haboobs are not just dramatic. They can be dangerous for drivers, aviation, and respiratory health, and they can arrive rapidly with little warning. They are a reminder that storms do not only move water, they can also move the land itself, lifting the ground into the sky. Lightning can travel through plumbing, wiring, and even phone lines. When lightning strikes a structure or nearby ground, it is not only a flash in the sky. It is an enormous electrical surge looking for paths that conduct well. Metal wiring,
pipes, and even connected lines can provide those parts, carrying current into places you would not expect. This is why storm safety advice warns against using corded electronics and avoiding contact with plumbing during a close lightning storm. A strike can send voltage spikes through electrical systems, damaging appliances or creating dangerous conditions. Even if the building itself is not visibly hit, water in pipes can conduct, and metal fixtures can become part of a route, especially in older systems with more conductive connections.
The idea feels unsettling because it turns the home into a network where the storm outside can reach indoors through infrastructure designed for comfort. Yet, understanding it is empowering. It explains why indoors is safer than outside, but not perfectly immune. The safest approach is to let the storm pass without turning yourself into a bridge between conductive parts of the house. Lightning is fast, opportunistic, and unbothered by walls. The safest place in a storm is a substantial building or hardtop car. Storm safety can sound simple, but it rests on deep physics. A substantial building offers shielding because its wiring and structure can help guide electrical current safely to the ground if lightning strikes nearby. A hardtop car works in a different way. The metal body acts like a cage that rips current around the outside rather than through the occupants, as long as the windows are closed and you are not touching metal parts.
This is why convertibles and open vehicles are not considered safe shelter, and why standing under a lone tree or in an open field is risky. The goal is to avoid becoming the tallest object and to avoid offering lightning an easy path through your body. Cars also protect you from wind-driven debris better than many outdoor shelters, though they are not safe in flooding. The calm feeling of a car during a storm is earned. You may hear thunder, see flashes, and feel rain pound the roof. But the structure around you is doing real protective work in a world where storms can change the environment in seconds. Good shelter is one of the most practical pieces of science you can carry with you. The 3030 rule helps judge lightning danger by thunder timing. Lightning safety often comes down to timing because the gap between flash and thunder is a quick clue to distance. When you see lightning, you start counting, and when you hear thunder, you stop. If that delay is 30 seconds or less, the lightning is close enough that you should already be in a safer place because storms can strike outward beyond the rain. The second part of the rule matters just as much. After the last thunder, you wait 30 minutes before resuming outdoor activities. This is because storms do not always end neatly. Lightning can continue even as rain weakens, and dangerous strikes can occur on the trailing edges while the sky looks brighter. The rule is memorable because it transforms a complex hazard into something anyone can do with their own senses. No apps required. It also teaches a subtle truth. The loudness of thunder is not the reliable metric. Distances. Thunder can be muffled. Wind can carry it away. And your ears can be fooled. Counting keeps you honest. It makes storm safety feel less like guesswork and more like a simple rhythm, a habit that can prevent tragedy. Storms can trigger landslides when soil becomes heavy and unstable. A hillside can look solid for years, then fail in minutes when water changes its internal balance. During heavy rain, water seeps into soil and rock layers, adding weight and reducing friction, like lubricating a stack of loose materials. If the ground is steep,
fractured or already saturated from earlier storms, it can reach a tipping point where gravity finally overcomes resistance. The result can be a landslide that moves as a slow slump or as a fast, roaring flow of mud and debris. These debris flows can carry rocks, logs, and soil like a thick river, bulldozing through channels and sometimes across roads and neighborhoods. Wildfire scars are especially vulnerable because burnt vegetation no longer holds soil in place, and the ground surface can repel water at first, sending more runoff down slope. Landslides are frightening because they can happen with little warming, especially at night or during intense rainfall, when you cannot see the slopes clearly.
They also show how storms shape the earth in a literal way. Rain is not only weather, it is a geological force. In the right conditions, a storm can rearrange a landscape faster than many people imagine possible. Floodwaters can rise faster at night when warnings are harder to notice. Night changes how people perceive danger. Visibility drops, routines slow, and the clues that something is wrong can be missed. In a flash flood, water can surge quickly through low areas and drainage channels. And at night, it can be harder to judge depth and speed. A shallow-looking sheet of water can hide a strong current or a washed-out road. Drivers are especially vulnerable because headlights flatten the scene, making it difficult to see that the road has become a moving stream. Sleep adds another risk. People may not hear distant sirens or may underestimate the urgency of a warning when they are groggy. This is why flood messaging often emphasizes not driving into water, and why communities push alert systems that can wake people. Flooding at night also interacts with infrastructure. Storm drains can clog, creeks can jump their banks, and water can back up into neighborhoods quietly until it is suddenly inside homes. The darkness does not cause the flood, but it removes the early visual feedback that helps people respond. In that sense, night acts like a veil, and floods are most dangerous when the veil is thick. Urban areas can amplify rainfall by warming air and adding aerosols. Cities change the atmosphere above them in ways that can influence storms. Concrete and asphalt absorb heat during the day and release it slowly, creating warmer air over urban cores, especially in the evening. Warmer air rises more easily, which can enhance upward motion when humid air is present. Cities also add aerosols, tiny particles from vehicles, industry, and everyday activity. And those particles can act as seeds for cloud droplets. The result is not a guaranteed storm, but a set of ingredients that can subtly alter how clouds form and where precipitation becomes most intense. Some studies have found patterns where storms intensify downwind of major metropolitan areas, shaped by the way urban heat and airflow interact with the larger weather environment. From a human perspective, this is fascinating and a little unsettling. It suggests that our built landscapes do not only respond to weather, they can nudge it too. Streets, rooftops, and smokestacks become part of the local climate system, influencing how moisture rises and condenses. A city can act like a gentle storm amplifier, turning the sky above it into a slightly different kind of theater than the countryside. Storm drains can turn streets into rivers in minutes. A storm drain is designed to quietly swallow rainfall, but it has limits. And when those limits are reached, the street becomes the channel instead. In intense downpours, water can arrive faster than drains can carry it away, especially if leaves, trash, or sediment block the openings. Once water begins to pool, it spreads quickly over flat pavement, finding low points and flowing along curbs like a shallow stream. Underpasses, dips in roads, and poorly graded intersections can fill first, creating deceptively deep pockets. In some situations, drainage systems can become overwhelmed as pipes fill, turning drains into unexpected fountains that force water back onto the streets. This swift change can take people by surprise because it does not depend on a nearby river spilling over. It is a localized flood, created by the imbalance between how fast rain falls and how much water the system can carry away. The risk goes beyond getting wet. Fast-moving water can carry debris, conceal hazards, and disable vehicles.
In urban settings, a storm does not need a canyon to form a river. It can carve one through streets and intersections in minutes. Storm waves can also reshape coastlines in a single powerful event. Shores may appear permanent, but an intense storm can rearrange them like a hand smoothing sand. When winds blow over the ocean for long periods, they build large waves that carry tremendous energy. As those waves reach shallow water, they steepen and break, delivering force to beaches, dunes, and cliffs. Sand can be stripped from one place and deposited somewhere else, sometimes forming new sandbars or cutting new inlets. Dunes that protected inland areas can be flattened and barrier islands can shift, altering how future storms impact the coast. Even rocky shorelines can be affected, with waves prying at fractures and accelerating erosion. The dramatic part is how fast it can happen.
A coastline that looked one way before the storm can look noticeably different afterward, with missing beach, collapsed dunes, or a changed shoreline curve. This is why coastal communities track erosion and rebuild dunes. They are living on the edge of a landscape that moves. Storm waves are not just water motion. They are sculpting tools, converting wind energy into geology in real time. Lightning can shatter trees by exploding sap into steam. When lightning strikes a tree, the damage is often not just from heat on the surface. It is from what happens inside. Trees contain water-rich sap, and a lightning current can heat that moisture almost instantly, turning it into steam. Steam expands violently, and that rapid expansion can split wood fibers, strip bark off in long ribbons, and even blast chunks outward. This is why a lightning-struck tree can look as if it has been peeled or cracked open, with scars that spiral upward along the trunk.
The strike may follow the path of least resistance, sometimes moving along wet outer layers, sometimes through internal channels, and the exact pattern can vary from tree to tree. Beyond the dramatic visual damage, a strike can also weaken the tree structurally, making it more likely to fall later in wind. For anyone nearby, it is a reminder that lightning is not only an electrical event, it is also a rapid heating event capable of turning water into an explosive force. A tree seems sturdy and slow-growing. Yet, in a fraction of a second, a storm can turn it into splintered debris. It is a powerful example of how storms can translate invisible energy into sudden physical change. Some storms form training bands that repeat over the same location. When storms train, they behave like cars on a track, one after another, rolling over the same stretch of ground. Instead of a single downpour that moves on, rain bands line up along a boundary in the atmosphere and keep regenerating upstream, then passing over the same town again and again. The sky can look almost steady, yet the rainfall totals climb relentlessly because the storm's conveyor belt does not shift.
This setup can happen when winds at different heights align in a way that keeps new cells forming where warm, moist air is lifted, while older cells drift along the same path. For anyone underneath, it can feel like the storm has decided to camp. Streets begin to pond, creeks rise, and the ground loses its ability to absorb more water. The danger is sneaky because each burst can seem manageable, but repetition turns just more rain into a flash flood risk. Training is one of the clearest examples of how storm motion matters as much as storm intensity. A storm can drop hail while the ground temperature stays warm.
It can be an odd moment, standing in warm air while ice rattles down around you. That happens because hail is made high in the storm, in air that is far colder than the surface. A strong updraft keeps hailstones aloft while they grow. Then gravity finally winds, and they fall through warmer layers on the way down. If the hailstones are large enough, they do not have time to melt completely before reaching the ground. Even when the air near you feels like summer, sometimes hail is scattered in bursts, as if the storm is shaking a bag of ice, because pockets of hail are released from the storm core in pulses. You might notice that hail often arrives with a sudden wind shift or an abrupt increase in rain intensity because it is tied to the storm's most vigorous regions. The warm ground does not stop hail. It simply tries to melt it, and the hail's size and speed decide who wins. It is a vivid reminder that a thunderstorm contains multiple climates stacked on top of each other. The color of a storm sky depends on light scattering and raindrop size. Storm light can look bruised, golden, slate gray, or almost black. And much of that comes down to how sunlight is filtered on its way to your eyes. Thick clouds block and scatter light, and the angle of the sun changes which colors survive the trip. Late-day sunlight travels through more atmosphere, which can remove more blues and leave warmer tones that can make storm edges glow. Raindrops and cloud droplets also matter. Different sizes scatter light differently, and heavy precipitation can act like a moving filter, dimming the scene and flattening contrast. Even the background behind a storm matters, because a bright sunlit field can make the rain curtain look darker, while a shaded landscape can make the same storm look softer. Dust or smoke in the air can tint the whole sky, changing a storm's palette before the first drop falls. None of this is the storm choosing a color. It is physics and perspective. Sunlight threaded through water and air, yet the result feels emotional, as if the sky is painting mood onto weather. Greenish stormlight often comes from sunlight filtered through deep water clouds. A green-tinted sky can feel eerie, and it often appears when the atmosphere is packed with water and the storm is thick enough to reshape the color of incoming light. One common setup is late afternoon or early evening, when the sun is low and its light is already warmer and redder than midday. When that light passes through a deep storm cloud full of water and precipitation, parts of the spectrum are absorbed and scattered in complex ways. If the storm is also producing heavy rain or hail, the amount of water and ice can increase the filtering effect, sometimes giving the underside of the cloud a greenish cast. The green color is not a guarantee of a tornado, but it can show up in storms that are intense and moisture-rich, which is why people often associate it with severe weather memories. The effect can also depend on what is behind the storm. A bright, sunlit background can make the filtered light look more pronounced. When the sky turns green
It is the atmosphere acting like a gigantic stained glass window, with water playing the role of colored glass. Thunderstorms can create sudden temperature drops called cold pools. A cold pool is a storm's footprint on the air itself, a spreading patch of cooled air that can outlive the loudest thunder. It forms when rain falls into drier air and evaporates, stealing heat and chilling the air, or when melting hail and snow cool the surrounding environment. That cooled air becomes denser, sinks, and then spreads along the ground like a slow wave. If you've ever felt a sharp chill arrive ahead of the rain, or noticed the wind suddenly shift and strengthen, you may have felt the leading edge of a cold pool. This pool can change how the storm behaves by cutting off warm inflow in one spot and forcing new lift in another. It can also travel away from the storm and influence the next hours of weather, sometimes helping new storms form along its boundary. In the evening, cold pools can make a hot day end abruptly, as if someone opened a door to a cooler room. They show that storms do not only drop water, they rearrange temperature and wind near the surface, creating new mini-environments that can spread across neighborhoods. Tornado damage paths can skip like a hopping footprint. Tornadoes do not always draw a neat, continuous line of damage. Sometimes the track looks like a series of separate marks, as if the tornado touched down, lifted briefly, then touched down again. This can happen because the vortex is constantly changing, tightening and weakening as it interacts with the parent storm and the terrain below. A tornado may become narrow and intense for a moment, then broaden, then lift slightly while still spinning aloft, then reattach to the surface farther along. Wind patterns around the tornado can also create odd damage contrasts with intense suction and debris impacts in one pocket and much lighter effects nearby. For investigators, these patterns are clues helping reconstruct the tornado's evolution second by second. For the people who lived through it, the skipping can feel uncanny. One street is devastated, while the next looks almost untouched. Like the storm made choices. It did not, but the physics can produce that impression. A tornado is not a solid drill bit carving the ground. It is a living, shifting circulation that sometimes brushes the surface and sometimes presses hard into it. Waterspouts are tornado-like vortices over water, often less violent. Over warm water, you can sometimes see a slender, spinning column connect cloud base to the surface, with a spray ring at the bottom, like a tiny storm making a splash. Many waterspouts form differently from the most destructive land tornadoes. They often begin near the surface and build upward, fed by gentle rotation and a favorable environment over water. Because of this, many are weaker than major tornadoes, though they can still be dangerous for boats and coastal areas. Waterspouts can look delicate, even graceful, yet they are real wind vortices capable of tossing gear, capsizing small craft, and reducing visibility with spray. Occasionally, a waterspout can move ashore and become a land tornado, sometimes strengthening, sometimes fading, depending on what it meets. Seeing one can change how you think about rotation in the atmosphere. You do not need a dramatic supercell to get a spinning column. Under the right balance of warmth, moisture, and convergence, the atmosphere can spin up a visible vortex in a surprisingly small space. It is the ocean and sky briefly agreeing to draw a spiral you can actually see. Landspouts form differently than classic tornadoes from stretching weak rotation. A landspout can appear suddenly beneath a developing thunderstorm, often as a narrow, ripple-like funnel. And it does not always need a powerful rotating supercell to exist. Instead, it can form when there is weak rotation already present near the ground, perhaps along a boundary where winds shift or converge. As a young storm's updraft grows overhead, it can stretch that weak rotation upward like pulling taffy,
tightening it into a stronger spin. If it becomes organized enough, a visible funnel may form, sometimes with dust and debris at the surface.
Landspouts can be brief, but they can still damage structures, uproot small trees, and surprise people because they may form in storms that do not look especially dramatic at first glance. They are a reminder that tornado-like phenomena come in more than one recipe. Sometimes the storm's job is not to create rotation from scratch, but to concentrate what is already there. Watching a landspout is like watching the atmosphere take a faint, invisible twist and suddenly draw it into focus, turning subtle wind patterns into a visible spiral. Some storms spin up brief gustados along outflow boundaries. Along the leading edge of a storm's outflow, the wind can surge and shear, creating tiny whirlwinds that form quickly and fade quickly. These are often called gustadas, and they are more closely tied to the storm's rushing cool air than to the deep rotating core that produces most tornadoes. They can look like short-lived swirls of dust and debris along a gust front, sometimes appearing in clusters, popping up and vanishing as the boundary moves. While many are weak, they can still knock over lightweight objects, damage small structures, and startle anyone who sees rotation and assumes it must be a tornado. The key difference is how they are connected. Tristanas are usually shallow and boundary-driven, not rooted in a strong storm-scale circulation. They often form where winds collide or where the outflow curls around an obstacle, creating a brief, spinning pocket. In a way, they are the storm's turbulence made visible. They show that a storm's leading edge is not just a cool breeze. It is a complex, shifting line where air masses fight for space. And sometimes that fight briefly creates a spin. You can see lightning frequently strikes before the heaviest rain even arrives. A storm can announce itself electrically before it truly opens the faucets. Lightning often begins when the storm's upper regions become active with ice collisions and charge separation, even while the surface below is still waiting for the main downpour. From the ground, this can feel like a warning shot. You see flashes, maybe hear distant thunder, yet the air around you remains dry or only lightly sprinkled. This matters because people often use rain as their cue to seek shelter. But lightning does not wait for that cue. The storm's electrical machinery can reach full operation while the rain is still building or still falling elsewhere inside the cloud. Sometimes, the first strikes occur on the storm's forward edge or beneath the spreading anvil, places that may not look threatening to someone watching the horizon. Then the rain arrives later as the storm core moves in and the precipitation shaft thickens. This sequence is one reason the first flash is a moment to take seriously, not a moment to keep playing outside until it starts pouring. The storm's timeline is not always what you expect. Electricity can lead and water can follow. Storm clouds can loft pollen and microbes high into the atmosphere. A thunderstorm is not only lifting water, it can also lift tiny passengers from the surface and carry them far above the world we live in. Strong updrafts can scoop up pollen grains, fungal spores, bacteria, and other microscopic particles from fields, forests, and cities. Then, loft them into cloud layers where the air is cold and fast-moving. Some of these particles can travel long distances before settling back down, which means storms can help shuffle biological material across regions. In some cases, those tiny hitchhikers can influence the storm itself. Certain particles can act as seeds for cloud droplets or ice, affecting how clouds form and how precipitation develops. It is a strange loop, living material rising into the sky and then helping shape the sky's behavior. For people with allergies, this lifting and spreading can also matter, because changing particle distributions can affect what ends up in the air you breathe. A storm, in other words, can be both a weather event and a biological delivery system, lifting the invisible into the high atmosphere and carrying it onward. Rain can carry desert dust across oceans, fertilizing distant forests. A storm can begin with dust. Winds can lift fine mineral particles from dry regions and inject them into the atmosphere, where they can ride high currents for astonishing distances. When those dust-laden air masses encounter clouds and rainfall, the particles can become captured inside droplets and carried back down to the surface. This is one way deserts quietly nourish distant ecosystems. Elements such as phosphorus and iron are limited in many tropical soils because frequent rain washes nutrients away over long periods. Dust delivered by rain can supply a new, subtle stream of those nutrients, helping support plant life in regions that appear entirely disconnected from their desert origins. You can sometimes notice the trace left behind, a faint film on cars or windows after rain, a quiet reminder that the sky is moving fragments of one landscape into another. This also affects ocean life. Dust deposition can supply nutrients that stimulate phytoplankton growth in certain regions, influencing marine food webs. It is a beautiful kind of planetary recycling, where storms act as couriers, carrying powdered rock from one continent to feed life on another. Thunderstorms help make nitric compounds that naturally fertilize soil. Lightning is not only light and sand, it is chemistry. The intense energy of a lightning channel can break apart nitrogen and oxygen molecules in the air and encourage them to recombine into new compounds, including nitrogen oxides. Those compounds can later transform into nitrates and related forms that dissolve in water and come down with rain. When that rain reaches soil, it delivers a small but meaningful dose of plant-usable nitrogen, one of the key nutrients life needs to build proteins and grow. Long before industrial fertilizers existed, this was one of nature's ways of turning abundant atmospheric nitrogen into something ecosystems could use. The amounts from any single storm are modest, yet over time and across landscapes, the effect adds up as a background source of fertility. This is why storms have often been associated with a feeling of renewal in farming cultures, not only because they water the ground, but because they change the chemistry of the air and deliver that chemistry to the roots below. In a quiet way, a thunderstorm can help feed the next season's green growth with nitrogen made in a flash. Storms can cool ocean surfaces, briefly changing local climate patterns. When a powerful storm crosses the sea, it does not simply skim the surface. Strong winds churn the upper ocean, mixing warmer surface water with cooler water from below. At the same time, heavy rain can freshen the surface layer, changing how easily it mixes and how it exchanges heat with the air above. The combined effect is often a noticeable cooling wake left behind the storm. A patch of cooler water that can persist for days or even weeks, depending on currents and sunlight. This cooling can matter immediately, because it can reduce the storm's own fuel if the cyclone loops back over the same region. It can also influence nearby weather by altering evaporation rates and the temperature contrast between ocean and air. Fishermen and oceanographers pay attention to these changes because surface temperature shifts can affect marine life and currents. What is striking is the timescale. The ocean, which we think of as slow and steady, can be rapidly reshaped at its surface by a single storm passage. For a brief window, the storm leaves behind an ocean memory, a cool imprint that affects what the atmosphere does next. Ancient people tracked storms by animal behavior, stars, and sky halos. Long before radar and satellite images, people still watched the sky with careful attention because survival depended on it. Coastal communities learned to read swell patterns and wind shifts as warnings of changing weather. Farmers watched cloud shapes, humidity, and the feel of the air on skin. Many cultures noticed that certain halos around the sun or moon often preceded stormy periods. A clue linked to high, thin ice crystal clouds that can arrive ahead of major weather systems. Observers also used the stars, not as storm predictors directly, but as navigation for seasonal timing, learning when certain rainy periods tended to arrive each year.
Animal behavior became part of the story too, because shifts in pressure, humidity, and wind can change how insects fly, how birds feed, and how livestock behave. Not every sign was reliable, but the practice of close observation built a kind of practical meteorology shared through stories and sayings. There is something beautiful in that. Storm tracking was once an intimate relationship with patterns in nature, a nightly habit of noticing small signals that hinted at what the sky might do next. Sailors once feared St. Elmo's fire, a glowing electrical storm effect. Imagine being at sea at night, with wind rising and clouds thickening, and then seeing pale blue light dancing on the tips of masts and rigging. That eerie glow is St. Elmo's fire, a form of electrical discharge that occurs when the electric field around an object becomes strong enough to ionize the nearby air.
It is not a lightning strike, but it is a sign that the atmosphere is highly charged, often in the presence of thunderstorms or electrified clouds. To sailors centuries ago, it could feel like an omen, a supernatural flame clinging to the ship, especially in the dark when the glow is most visible. Today, we understand it as corona discharge, a cousin of the same electrical processes that produce sparks and lightning, but gentler and more continuous. It can appear on airplane wings too, or on other pointed structures wherever electric fields become intense. The fear makes sense when you picture the setting: a glowing mast, a heaving sea, and a storm brewing nearby. St. Elmo's fire is the atmosphere whispering, not shouting. Yet it speaks clearly that electricity is building in the sky. Some storms have lasted for days, reshaped by new bursts each night. Not every storm is a quick drama with a tidy ending. Some systems persist and reinvent themselves, especially when the atmosphere keeps providing moisture and instability. In warm seasons, long-lived storm complexes can weaken during the day's transitions, and then flare again after sunset, when low-level winds strengthen and feed humid air into the system. Each new burst of convection can reshape the storm's structure, creating fresh rain cores, new wind surges, and changing lightning patterns, even if the overall system remains in place. Over the ocean, a tropical disturbance can repeatedly organize and lose organization while still surviving, waiting for a better moment to consolidate. Over land, a stalled front can act as a scaffold, allowing repeated rounds of storms to form along the same zone for multiple days. For people under such a pattern, time becomes part of the hazard. Infrastructure wears down,
soils saturate, and fatigue sets in because the weather never fully clears.
These multi-day storms show the atmosphere's endurance. The sky can keep building new chapters from the same ingredients, especially at night when the air's hidden rivers of moisture often become more active. Climate change can intensify heavy rainfall because warmer air holds more water. Warm air has a greater capacity to hold water vapor, and that simple physical relationship helps explain why heavy rainfall events can become more intense in a warming world. When the atmosphere contains more moisture, storms have more raw material to condense into rain, which can increase the potential for intense downpours when conditions trigger strong lifting. This does not mean it rains more every day, everywhere. It means that when storms do form and tap into humid air, they can produce heavier bursts of precipitation, raising the risk of flash flooding in vulnerable areas. The effect is often most noticeable in extremes, the days that already bring major rainfall, becoming even more capable of overwhelming drainage systems and waterways. Local outcomes still depend on regional patterns, oceans, winds, and terrain. So the story varies from place to place, but the underlying physics is steady, like adding more water to a sponge that will eventually be squeezed. When the storm squeezes, more water can come out at once. This is why scientists and city planners pay attention not only to average rainfall, but to how the strongest events may shift, because those are the ones that test bridges, dams, and neighborhoods most sharply. Storm scientists chase tornadoes to measure winds and improve warnings. The image of a storm chaser can look like pure adventure, but the deeper purpose is often data. Scientists and specialized teams position instruments in and near storms to measure wind, pressure, temperature, humidity, and debris patterns, because real-world measurements help refine how we understand tornado formation and behavior. Mobile radar units can scan rotating storms at close range, revealing thinner-scale structures that distant radar cannot always resolve. Probes can record sudden pressure drops and wind shifts near the surface, where tornadoes actually interact with buildings and landscapes. Every good dataset becomes part of better forecasting tools and better warning strategies, helping communities gain minutes that can save lives. The work is difficult because tornadoes are unpredictable and dangerous, and the best measurements must be taken without becoming part of the storm's damage. There is something inspiring about that balance. Curiosity paired with caution. Storm science is not only equations and models, it is also people in the field listening to the atmosphere with instruments trying to turn chaos into knowledge that protects others. Each chase at its best is a careful mission to understand the most intense winds on Earth. Every storm is a heat engine, turning sunlight into wind and rain. Storms feel sudden, but their energy story begins quietly with sunlight warming oceans, lakes, land, and air. That heating drives evaporation and creates temperature differences, and those differences are stored energy waiting to move. A storm releases that stored energy by lifting warm, moisture-laden air and allowing water vapor to condense, turning invisible heat into motion and falling rain. As air rises, it draws more air upward from below. As winds intensify, they sculpt the storm's structure, guiding rain bands, forming gust fronts, and at times, organizing rotation. The rain that eventually reaches the ground is more than water returning to Earth. It is the visible conclusion of an energy journey that began with the sun and moved through evaporation, uplift, and condensation. In this way, A storm is a machine built only from air and water, yet capable of significant work, shifting vast air masses, reshaping coastlines, and nourishing ecosystems. Thinking of storms as heat engines makes them feel less like random tantrums and more like the atmosphere's way of redistributing energy across the planet. The sky is constantly balancing its books, and storms are one of its most dramatic transactions. As our journey through storms begins to settle, you may notice how vast and connected it all feels. From towering clouds rising on warm air, to lightning stitching sky and ground together, to rain carrying stories from oceans, deserts, and distant forests. We wandered through spinning winds, hidden electrical worlds, drifting dust, and the quiet chemistry that feeds the soil after thunder fades.
Storms revealed themselves not as chaos, but as conversations between heat and air, water and motion, sunlight and night. Now there is no need to hold on to the details. Let them drift like clouds thinning at dusk. Imagine the storm moving away, rain softening into a steady rhythm, wind easing into a gentle hush. The sky grows darker, calmer, and the world feels rinsed and renewed. Your breathing can slow, your shoulders can rest, and your thoughts can become as light as mist. If you found comfort or curiosity in this gentle exploration, you're always welcome to like, subscribe, or leave a quiet thought below. It helps others discover these calm corners of science, one peaceful moment at a time. And if you find yourself still awake, another video will be waiting on the screen, ready to carry you onward with a new story and a softer pace. For now, let the images fade. Let the last echoes of thunder roll into silence. Feel the ground steady beneath you, the air cool and still. Nothing more is asked of you tonight. Just rest, breathe, and allow sleep to arrive in its own time. Sleep well, and good night.